Alright, so let's see how C mode works in a cell. So I'm going to show a picture of a basic cell. And as we already know, there are D inputs and outputs on each side, which I will indicate with these dark arrows. But then there are additional inputs and outputs on each side, which are labeled C, and I'm going to draw the C lines in red as such. And for the most part, we're not going to pay a lot of attention to the C lines, but there are a few operations where these are going to come into place. So as a very simple example, if I were to apply a 1 to a C input on this side of the cell enters C mode, and there's a system-wide clock, and every time the clock ticks, the next bit of the cell's truth table is going to be sent on this D output. And whatever bit is coming in on this D input will populate the truth table in the position of the bit that was just sent out. So we can read the contents of a cell by putting a 1 into the C input and looking at the D output, and we can also populate the contents of a cell's lookup table by putting a 1 into the C input and supplying bits onto the D input. Now, how do we supply our bits? Well, there's a few ways. Let's take a look at a 2-cell circuit, and all of these connections are set up in the way you would expect, but I'm going to just draw a few of them. And I'm going to set this cell up to put a 1 into the C input of its neighbor, and take the D line that's coming out and pass that over to the western edge of this cell. And now this cell here is reading the contents of this cell's truth table and sending a copy of that bit stream from its truth table out to its western side, where some other cell can be taking that bit stream and doing some processing with it. This is a useful way to read a cell's contents, but the problem with it is that unless we put something meaningful on the D input of this cell, we're just filling up its truth table with zeros. In other words, it's a destructive read. Now, if we put a pattern of 1s and 0s on this D input, we could load the target cell's truth table with some sort of useful pattern. Well, a particularly useful pattern is simply a copy of the bit streams that we're reading out of that cell. So if this cell, which we call the controller, takes the D input from the target cell and resends it back into the D input of the target cell, in addition to sending a copy of that bit stream out to the west, it's now doing a non-destructive read on this cell. So as the system clock ticks, bits from this cell's truth table are sent out into this controller. The controller copies them back into the D input. And the way the timing is set up, this happens in a way that causes the truth table in this target cell to not be disturbed. In other words, the bits are sent out before the new bits coming in need to be available. And so this is a non-destructive read. We take a copy of this cell's truth table and we send it out to the west. Now, we can make this a little more interesting by putting another cell over here, and we'll send the D bits that we're reading from the target cell into the D input of this cell. But we're also going to send a 1 into the C input of this source cell. So we'll call this the source. We'll call this the controller, and we'll call this the target. And now as the clock ticks, bits are read out of the target cell. They're recirculated back into the target cell, so it's non-destructively reading the cell's truth table, but it's also sending a copy of those bits into the source cell. And since it's asserting 1 on the source cell's C input, this cell's truth table is now being replicated into the source cell. In the case of 4-sided cells, there's 128 bits in the truth table. It takes 128 clock ticks to read all the bits of this cell's truth table, and after 128 clock ticks, this cell will be an exact clone of that cell. So whatever function this cell was set up to perform, this cell has now been configured to perform the same function. So this is a non-destructive cell replication operation.